Welcome to This Explainer. Today, we're diving into exactly why our beautiful blue planet is, well, considerably more complicated than the simple thermostat sitting on your living room wall. We so often hear climate discussed as if Earth just has this one simple temperature dial that goes up and down. But right now, we're going to peel back the curtain and look at the massive, intricate spreadsheet of variables that Mother Nature has actually been balancing for billions of years.
Okay, let's just tackle this funny, kinda sarcastic premise right out of the gate. Apparently, Earth's climate has always been perfectly well behaved. It's a crazy thought, isn't it? This idea that before recent human history, Earth was just cruising along at a perfectly pleasant, completely static temperature. But as you'll see in a minute, our planet has historically been anything but perfectly well behaved.
I mean, we are talking about a dizzying list of absolute chaos here. We've seen massive ice ages, brutal volcanic winters, and times when the poles were literally tropical. No joke. The reality completely shatters the idea of a static, normal baseline. Earth is constantly dealing with retreating ice sheets, shifting continents, and what we can really only call occasional meteorological tantrums. It is, and it always has been, an incredibly dynamic system.
So, let's kick things off with Section 1, the cosmic metronome, looking at space and astronomical forces. You know that giant nuclear reactor up in the sky? The sun goes through roughly an 11-year cycle where its magnetic activity and ultraviolet radiation fluctuate. But here's the crazy part. The overall change in its total solar energy output during that cycle is just a relatively modest 0.1%. Now, that might sound tiny, but in the grand equation of Earth's climate, it is a vital, ever-changing piece of the puzzle. And then we have the famous Milankovitch cycles, basically Earth's astronomical metronome. First, the wobble. Earth actually wobbles just like a cosmic spinning top, changing the direction of its axis over roughly 26,000 years. Step 2 is the tilt, which slightly shifts back and forth over 41,000 years. And finally, Step 3, the actual shape of our orbit, stretches out and pulls back in over 100,000 years. This non-stop geometric shifting continually alters exactly where and when solar energy hits our planet.
Oh wait, there's more. On top of all that spinning and wobbling, we have to remember the big picture. We aren't just sitting in some sealed, controlled laboratory with the outside variables turned off. Our entire solar system is hurtling through the Milky Way. We are actively moving through interstellar space, constantly exposed to changing cosmic radiation and interstellar material. We are very much a part of the vast universe around us.
Moving right along to Section 2, Earth's internal mood swings, our internal feedback loops.
Let's talk about the oceans. They essentially act as the world's biggest heat storage unit. They absorb massive amounts of solar energy and churn it around the globe, but they definitely don't operate in a straight line. We have these irregular cycles kicking in roughly every 2 to 7 years, known as El Niño and La Niña. El Niño can temporarily spike global temperatures up, while La Niña drags them down. So when someone asks why a particular year felt unusually hot or cold, sometimes the answer is simply that the ocean was having a bit of a dramatic mood swing.
And then, every once in a while, Earth just decides to pop a giant pressure release valve. Major volcanic eruptions blast immense amounts of sulfur compounds high into the atmosphere. This basically acts like a massive planetary shield, reflecting sunlight and causing some serious temporary global cooling. In 1815, Mount Tambora erupted, directly leading to 1816 being famously known as the year without a summer. Imagine literally canceling summer because a volcano couldn't keep a lid on it. Mount Pinatubo did a very similar thing to global temperatures back in 1991.
Now, throw ice into the mix. It basically operates as Earth's giant solar mirror. It's a beautifully logical feedback loop. More ice means more reflected sunlight, which causes more cooling. On the flip side, less ice means darker oceans and land masses absorb more sunlight, which drives further warming. It sounds incredibly simple, right? Well, actually, scratch that, because this entire loop is intricately wired into the oceans, the atmosphere, clouds, and vegetation. Earth clearly doesn't believe in simple math.
Just look at the sheer scale of this natural operation. Mother Nature has been running this giant carbon recycling spreadsheet for billions of years. Plants and forests absorb CO2. Soils and oceans store and release it. Trillions of microorganisms shuffle it all around. Rocks lock it away for eons, volcanoes aggressively vent it back out, and the incredibly slow process of weathering removes it again. It's just a phenomenal, non-stop planetary balancing act.
As if that wasn't chaotic enough, let's add those harmless-looking fluffy things in the sky, clouds. They add some serious complexity to the equation because some reflect sunlight to cool the planet, while others trap outgoing heat to warm it. Oh, and Earth's very own internal compass? Over long geological timescales, our magnetic field wanders around, it gets stronger, it gets weaker, and occasionally the poles just completely reverse. No big deal, right?
Which brings us to Section 3, the human variable, a very fast-moving factor. So humanity has become a very distinct variable in this extraordinarily complicated system. Now, with 8.3 billion of us, you might think physical space is the main issue. But honestly, theoretically anyway, you could squeeze the entire human population into an astonishingly small area compared to the total landmass of Earth. Just standing around on the planet doesn't actually take up that much room. The absolutely crucial point here is that our real footprint, our true physical impact on this complex system, is our rapid daily activity. It's our massive energy demands, our sprawling agriculture, our global industry. But more than anything, it's the fact that we are taking massive quantities of fossil carbon from underground and moving it directly into the atmosphere. And we are doing it extraordinarily fast compared to those natural thousands and millions of years we talked about earlier. We have basically dropped a brand new, incredibly fast-moving variable right into the middle of Earth's delicate spreadsheet.
Let's zoom out for Section 4, a very complicated CV. 4.5 billion years of extreme weather.
I mean, if Earth handed you a resume, it would be absolutely wild. It has been way hotter than it is today, and way colder. It's been entirely covered by enormous ice sheets, and it's also been so warm you'd find tropical conditions near the poles. It's seen radically different sea levels and operated with completely different continents. And remember, all those radical, world-altering shifts happen without a single human being around to file a planning application. Earth has literally seen it all.
People so casually talk about the climate as if it's just a single dial on a dashboard. But as we've seen, it's a wildly complex system of variables operating on totally different timescales. Clouds and weather, they change in days. El Niño cycles, a few years. Deep ocean circulation and heavy human impacts play out over centuries. Those astronomical Milankovitch orbital cycles take tens of thousands of years, and things like continental drift take millions to billions of years. All of these different dials are spinning at completely different speeds, all at the exact same time, while the Earth just keeps on turning.
So, what's the big takeaway here for this explainer? The most common question people tend to ask is the climate changing? But honestly, of course it is. It literally always has. So instead of asking if it's changing, the real questions we need to ask are, what is changing it, by how much, and over what timescale? Understanding the massive difference between a slow, natural 100,000-year orbital wobble and a hyper-fast century of intense human industrial activity is exactly how we make sense of our world. After 4.5 billion years, Earth has built one hell of a CV, and she's definitely seen worse weather than this. The only question now is which variables are going to dominate this next chapter. Thanks for diving into this incredibly complex spreadsheet with me. Keep asking the right questions, and I'll catch you on the next explainer.